Molly started her work in astronomy 2015, less than 10 years ago, and she's doing fantastic work now, as you can see with the imaging. Impressively, she's been involved in STEM outreach, some 160 hours to up to 50,000 people in person and in a virtual mode, which is really impressive. She's an ambassador to the American Association of Variable Star Observing and also Explorer Alliance. As I've mentioned, she's an accomplished astro imager. She's a panelist and broadcaster on the YouTube Astro Imaging channel. If you haven't been out there, you might want to take a look at that. Recipient of the Astronomical League's 2021 Wilhelmina Fleming Imaging Award, first place. Molly, that's a real accomplishment. Congratulations. And but that was the real happy note. If you haven't been out there, though, do check out the Astro Molly Imaging blog. It's a lot of good information out there. And also, you might want to take a look at our SVAS YouTube channel, because in 2020, she gave a great talk on astrophotography. It's the September talk, so you can go out to YouTube and find that. While working on her PhD, she holds a master's in nuclear engineering, which is a good segue into tonight's presentation, titled Origin of the Elements, a Story of Stellar Nucleosynthesis. So Molly, take it away.
Thank you so much for having me back. I missed being out there and seeing everyone at Blue Canyon. So I'm glad to come join this meeting again, even though it is quite late here in Ohio. At least it's a Friday night.
Well, we welcome you virtually.
Thank you. Yeah, so I'll go ahead and start sharing my screen here. This one, and then this button here. All right. So this is a talk I've given a few times in a few places. I gave it at the 2019, 18, 19, one of those two, Texas Star Party. And I've given it a few other times. Yeah, I think it was 2018 Texas Star Party. And it's one of my favorite talks, and I get to get into all kinds of really cool physics and kind of walk you through how all the elements in the periodic table have come to exist in the universe. Because if you sit back and think about it, we know that all the stuff is from stars, but we also know that stars fuse hydrogen into helium. So what happens after that? How do we get to lead from helium? So I'm going to go through all of that tonight. So here's the answer. End of talk. This is a really cool chart that I've found online, and I went back to go see if there'd been any updates, because there has been some updates in this area of research in the last couple of years, but it looks like this chart is still holding for the moment. So this kind of shows for each element in the periodic table, up at least through the ones that any one of the ones that are gray are man-made, so we don't even bother showing the last row of the periodic table, because those are also all man-made. And where they come from in terms of what physical processes are forming them. So I'm going to talk about some of these tonight and what's happening there exactly. All right, so before I can get into a lot of the fun stuff, we're gonna start with a little bit of particle physics. So this is a figure that represents what we call the standard model in physics. So this represents the known particles that make up all the other things. We have on the top of this circle the types of quarks, which have strange little names like up, charm, down. Physicists are weird. And those are, yeah, so we have the quarks. And then on the bottom half of the circle, the green ones, those are the types of leptons. So the one you're probably familiar with is the electron, which is a component of the atom, but there's also muons and tau particles, and then there's their neutrino counterparts. In addition to, so those are the particles. The blue circle are the force carriers, and I'm going to talk a little bit. I'm kind of glossing over a lot of stuff right now, but also known as gauge bosons, and these are what carry the 4 fundamental forces, which I'll get into in a bit. And then in the center we have the scalar bosons, which right now is just the Higgs boson, which you probably heard a lot about back in 2012 when it was finally observed at the Large Hadron Collider. And that has to do with how some particles have mass and some have a lot less mass. All right, so a little glossary of the particles that exist. So in the standard model, we had quarks and we had electrons as a type of lepton. So quarks, they come together and form hadrons, which include the possibly familiar protons and neutrons, which are the constituents of the nucleus of the atom. And a nucleus becomes an atom when it has some electrons attached to it. And that is what consists of all of the matter that we interact with. So all of the elements of the periodic table are types of atoms. And then from that, you build out to molecules, and that's how you get people and cars and planets and kitties. I've got my kitty cat sitting over here. All right, the other important component to understanding the rest of this talk are the 4 fundamental forces. So you're probably quite familiar with gravity. That's the one that keeps us down here on the surface of the planet and keeps the Earth in orbit around the sun and keeps the sun in orbit around the center of the galaxy, and so on and so forth. You may also be familiar with electromagnetism. So we have electricity, we have magnetism, but electromagnetism is also what is responsible for, like, your hands not just going through each other or you not falling through your chair. It's the repulsion of the atoms that make up all of these things. And above that are 2 forces you're probably less familiar with, which is the weak force, which is the main role that it plays is mediating beta decay, which I'm going to get into later. It's very important in how we get to all the stuff that is heavier than helium. And the strong force, which is what holds the quarks together and what holds the innards of nuclei together. And so the strength of these forces, gravity is the weakest, the strong force is the strongest, and the amount of difference between the gravitational force and the strong force is 10 to the power of 38. The strong force is 10 to the power of 38 times stronger than gravity. That's 10 with 38 zeros after it, which is just an insanely enormous number. It's you get to some crazy stuff there. All right, so let's start diving into the astronomy part of this. I'm going to do a walkthrough of the timeline from the Big Bang up to the modern era, and then we're going to look at what different points some of the lighter elements are made, including the very important hydrogen and helium that made it possible for stars to exist. So we have the Big Bang, and in times less than 10 to the minus 43 seconds, which is 0.43 zeros and then a 1 at the end. So very, very, very early times. This is called the Planck Epic because the universe was very, very tiny, smaller than can ever be physically measured. And then in the next little instant of time, 10 to the minus 36 seconds, is when the 4 fundamental forces are all the same. So gravity and the electromagnetic force and the weak force and the strong force they all act like the same force. This is what is known as grand unification, and kind of the grand theory of everything that that physicists are often seeking to see how these forces come together. At 10 to the minus 32 seconds, we have inflation. and space expands by a factor of 10 to the power of 26. Lots of just insane numbers in this talk, by the way, which is actually why I have to have a set of notes that I'm looking at for all this. Now, as you know, as you either remember from high school or have observed yourself when using something maybe like hairspray or a can of spray duster, when a gas expands, it cools. And so space expanded by 10 to the power of 26, and it's super cooled 100,000 times. So we go from temperatures of let's see. Yeah, we go from extremely high temperatures to still extremely high temperatures, but like less extremely high. And then I can get the slide to advance here. In the next time period, in 10 to the minus 12 to 10 to the minus 6 seconds. So we're still talking like picoseconds to nanoseconds here after the Big Bang. Still extremely small early areas of time. This is the quark epoch. So we have this quark gluon soup of just individual quarks roaming around. There's no nuclei, there's no atoms yet. This is before any of those exist because it's too hot. It's too hot for the quarks to come together. But the forces begin to separate. We have the gravitational force becoming one thing and the weak and strong electromagnetic force being another force. These are the highest energies we can directly observe in the Large Hadron Collider. And it's exceedingly difficult to make a collider that can go to any energies higher than this. Come on, slide advance. All right, next from 10 to the minus 6 seconds, so from 1 nanosecond to 1 second, this is the Hadron Epic. It's now starting to get cool enough that the quarks can combine into hadrons, aka protons and neutrons, which still they're still too hot to make a nucleus, but we have protons and neutrons, so that's cool. And we also have some other types of particles called mesons, which include pions and kaons and all these other exotic particles. Now, at this point, there's still matter and there's still antimatter at this point. And there's a very slight matter asymmetry. There's 100 million and 1 matter particles to 100 million antiparticles. And at this moment, we have annihilation. So it's just cool enough for these particles to exist independently, but then the particles and the antiparticles all annihilate, and we're left with all the particles we now have in the universe, 100 million times less than what there were because of this annihilation event. At 1 second, neutrinos stop interacting, and the universe is now roughly 10 light years across. So let's see, what's 10 light years across? It's like twice the distance from here to Alpha Centauri, for example. All right, in the next stage, we're now getting into units of time that we're maybe a little more familiar with, 3 minutes to 20 minutes after the Big Bang, which is Big Bang nucleosynthesis. It's finally cool enough now that protons and neutrons can now bind to form nuclei. So we have the potential to build the first atoms. They don't have any electrons yet, so they're ionized. They're not atoms yet. They're just the nuclei. But we have some nuclei now. Now, if you know anything about neutrons, you know that they can't exist on their own for very long. They have a half-life of 10 minutes. So if you have a free neutron floating around, it will decay on average in 10 minutes. But the universe is not yet that old, so there's still a lot of neutrons flying around. And I put this tidbit in here because I get asked this question when like, how did the neutrons come about? That was one of the first things when I was building this talk, like, that I was wondering, because in order to form helium, you have to have a neutron. Where do neutrons come from? So that's why they're still about. It's cool enough that hydrogen and helium and lithium, the first 3 elements of the periodic table, can now start to form. And after about the first 20 minutes, the temperature falls enough that fusion can't continue anymore. So we're not getting any more helium or lithium, but it's still too hot for the atoms to get any electrons, and the universe is still opaque to light. So light is just continuously being absorbed and re-emitted, and the light's not actually traveling through the universe yet at this point. All right, then we have a very long period of time. We now jump to 379,000 years, roughly, after the Big Bang. And this is the era of recombination. So the universe is cooled to about 3,000 Kelvin, which is about the temperature, it's a little cooler than the temperature of the surface of the sun, which is still hot, but much, much cooler than the, 10 to the power of 15 Kelvin, aka 10, what is that, quadrillion, quintillion Kelvin than it was earlier. That's cool enough to allow atoms to capture electrons and become neutral. This is really important because when those atoms become electrically neutral, so they don't have a charge anymore because they now have an electron with them, which cancels out the proton, and now they're electrically neutral, light can now pass freely through the universe. And this is the cosmic microwave background that you probably have heard a lot about. This is when it was emitted. Now, the temperature of the universe was 3,000 Kelvin at this point. So the cosmic microwave background when it was emitted was like visible light. It wasn't radio yet. That happens as the universe expands. At this point, the universe is a fog of about 75% hydrogen, 25% helium, and traces of lithium. But we don't have stars yet. The first stars don't form until after the first 150 million years after the Big Bang. And the time between recombination and these first light sources is known as the Dark Ages, which is actually a period that we're hoping to maybe see back as far as with the James Webb Space Telescope. So get excited. All right, so moving on from there, we're quickly starting to catch up to the modern era. Stars and galaxies start to form about 300 to 500 million years and onward. And when those galaxies form, gravity's kind of pulling clumps of primordial clouds of gas together. They become more dense. They start to come together under their own gravity to form stars. And then, and that's when you start being able to get hydrogen fusion to make those stars, which I'll get into in a bit. Now, these first stars are short-lived and explode as supernovae. They don't last very long, which produces a lot more elements, which we'll also get into. And then these large volumes of both stars and the matter that's been spewed from supernovae start to form into galaxies, and then the galaxies gravitationally interact to form groups, clusters, and superclusters. And we get the massive universe full of galaxies that we have today. All right, so let's step back a little bit. Let's talk about primordial nucleosynthesis. So this is, how do we get hydrogen and helium and lithium? So 3 to 20 minutes after the Big Bang, the universe is cool enough for the protons and neutrons to start forming hydrogen and helium. Now, hydrogen is just a proton. It does not have a neutron with it. So the hydrogen nucleus is just a proton. Helium is 2 protons and 2 neutrons. So you got 4 particles together. And then there's also a small amount of lithium, which in this case is 3 protons, 4 neutrons, and any other isotopes of these, so like lithium-6 and others nearby, are unstable and decayed away. So 75% helium, 75% hydrogen, 25% helium, trace amounts of lithium. And then nucleosynthesis stopped. There's not enough, the energy is not high enough to form any larger nuclei. There's not enough energy to fuse, say, 2 heliums together into a boron-8 or anything like that. Also, there are no stable nuclei that have a mass of 5, so that have like 5 protons and neutrons, or 8. This is really interesting and has some really serious implications for why nucleosynthesis stopped at this point and why stars are so important for us existing. All right. So now we get to hydrogen fusion. I'm going to skip over how stars form because we don't have time. There's so much other stuff to cover with the whole periodic table. You could do an entire talk on how stars form. It's super cool. All right, but basically, the heat, so once you have your star, the heat inside the star keeps the atoms ionized, which means that they're positively charged. But positively charged things repel each other, like two positive ends of a magnet. They push each other apart. However, if the nuclei are forced really close together, then that electromagnetic force that was repelling them gets dominated by the strong force, which is the force that pulls protons and neutrons together in order to form nuclei. The energy to do this, however, is higher than the energy available in the burning core of a star. It requires, and this unit's not going to mean anything to a lot of you, but it requires 1.2 mega electron volts to push the two protons together. Now, to put that in a unit, that might mean more to you. The temperature equivalent of 1.2 mega electron volts is 10 quadrillion degrees. Technically it's degrees Kelvin, but by the time you get to 10 quadrillions, Kelvin and Celsius and Fahrenheit are like all the same. So in the core of the sun, for instance, it's only 15 million Kelvin, which is way too cold to push those two protons together. So how does fusion happen? So without getting too heavy into the quantum mechanics, because this is where quantum mechanics starts to happen, due to how the particle wave duality stuff and the wave function of the proton can penetrate through the barrier, and there's a non-zero probability that the proton can tunnel through the energy barrier. So because of crazy quantum mechanics stuff, the proton can sneak over that energy barrier that it takes to push those two protons together. It can slip past it, and then you get fusion. It's crazy cool quantum mechanics stuff. This is called quantum tunneling. And oh yeah, I had that bit of a graphic there too. So it's skipping, going over that energy hump, and is cutting right through it to get into its ability to fuse with another proton. From there, we get what is known as the PP chain, PP for proton-proton. So we have two protons, which is really just, basically two hydrogen atoms that don't have their electrons, ionized, as we say. Those two fuse together, and then we get one. So you have the two protons, but two protons does not make a helium to a deuterium nucleus. As you see in the picture here, this atom here, known as deuterium, has a proton and a neutron. So what happens actually is that proton undergoes a process called beta decay, where it literally converts from a proton to a neutron, and in the process emits an electron or a positron. In this case, it's an electron, and a neutrino. Actually, no, sorry. In this case, it's a positron. My bad. And then the next step, that deuteron fuses with another hydrogen that's floating around, and you get helium-3, so two protons, one neutron, and that emits some energy. And then two helium-3s then fuse to form helium-4 and emit two more hydrogen atoms, which are now free to go participate in other fusion reactions. And we get to, so that's how hydrogen fuses into helium. You don't really get just like four particles coming together. There's a bit of a process that this goes through. Now, this is a busy graphic, but I'll go through it. That PP1 chain happens about 85% of the time, and that gets us helium. But actually, in addition to helium, in this early process, we also get some beryllium and some boron, the next two elements, and also some lithium. So the next three elements in the periodic table. So looking at the PP chain 2, which is the one kind of in the lower middle there. Sorry. Yeah, that's right. Okay. A helium-3 and a helium-4 from the PP1 chain combine to form beryllium-7, which emits some energy. And of course, this energy emission is important. That's how we get light and heat from the sun. From there, most of the time, it will capture another electron, yada, 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 lots more science. And eventually you get a lithium that decays to two more heliums. But you still got some lithium floating around. And then over on the PP3 side of the chain, you can actually get to boron-8, which immediately decays to beryllium-8, which immediately decays to helium-4s, because things with 8 protons and neutrons are unstable, because helium is so much more stable than them, and it just really wants to be helium. It just does. It's a quirk of quantum mechanics. All right, we'll get past there. Now, that gets us to a grand total of the first like 5 elements of the periodic table. Really only the first 3, because the beryllium and the boron decay away. So where do we go from there? Now, in the first stars, they were just fusing the hydrogen and the helium and then running out of fuel and exploding. But as more of the stars are running out of fuel and exploding and making stuff that's higher up on the periodic table, which I'll get to later, then we can start having stars that have carbon in them. And we can start going through what's called the CNO cycle, the carbon, nitrogen, oxygen cycle. Basically what's happening here is you start with carbon, and it goes around in the circle of a bunch of beta decays and releasing a bunch of energy. And it goes from carbon 12 to nitrogen 13 to carbon 13 to nitrogen 14 to oxygen 15 to nitrogen 15, back to carbon 12. In the process, it releases the helium, some hydrogen, and a whole bunch of energy. And so that's another way that stars that are on a little on the larger side, larger than 1.3 solar masses, that's how they get their energy once they burn through a lot of their hydrogen. So you might ask yourself, well, if this process starts and ends with carbon, where does the carbon come from? Good question. All right, so the carbon happens in a process called the triple alpha process. So as we saw earlier, some reactions produce beryllium-8 and lithium-5. Both of these are unstable, which will decay almost instantly back to lighter nuclei. But sometimes, if there is a helium floating around in the vicinity from another fusion reaction, there's just enough time for it to fuse with the beryllium-8 before the beryllium would decay away to produce carbon-12, which is that nice stable form of carbon that makes up all of us. Yeah, I'm gonna skip a couple notes here. So in stars that are running out of hydrogen to burn in their core, the core will start to collapse, and then it'll get really hot in the core. 100 million Kelvin, which is about 6 times the sun's core temperature. At this temperature and density, the heliums can fuse fast enough to produce significant amounts of carbon, and that finally restores some equilibrium to the core so it doesn't just continue to collapse. All right, from there we go up the chain. Carbon-12 plus helium-4 is oxygen-16. Oxygen-16 plus another helium is neon-20. And as you keep adding additional heliums, as it gets much hotter in the cores of stars, and my cat is now blocking my computer screen. Come over here, please, thank you. We get manganese-24, silicon-28, and much more. But that process stops at iron-56. It is not energetically really possible. I mean, it's technically possible, but it's not energetically favorable for stars to fuse anything heavier than iron-56. There's obviously a lot of elements in the periodic table after iron-56, which is, got this on my other screen. Iron. Yep, there it is. It's labeled 26 here because 56 is the total number of protons and neutrons. 26 is the number of protons. Okay. So to get to elements above that, that's where we have this process called the S process, which is short for slow neutron capture. This occurs in large stars as well as planetary nebulae. Planetary nebulae, like this one here. I think this is the Cat Eye Nebula. So you have to have a lot of neutrons around that are coming from various other reactions going on in the star, and slowly the elements that are existing will absorb neutrons, which will then beta decay and step up the periodic table that way by effectively converting neutrons to protons. And this process gets you about as high as lead. So we're working our way up there, but still not all the way through the periodic table yet. briefly back to here, you'll notice that, so I mentioned that, basically beryllium-4, some types of lithium and boron, beryllium-8 and boron-8, yeah, they get skipped when we're doing primordial nucleosynthesis and stellar nucleosynthesis. Those are actually made by a process called cosmic ray fission, where a high energy photon comes from elsewhere and fissions apart a heavier element, and that's how we get beryllium and boron. It's pretty cool. All right, so that only takes us up to lead. What happens after that? Supernovae. So supernovae happen for stars that are greater than 8 solar masses, and or at least the ones that have enough energy floating around in them to produce the much heavier elements. Now, as I was researching this, I saw a number that is just outstanding. The amount of optical light produced in a supernova, the amount of energy in that light is 10 to the power of 42 joules. Like, how much energy is that? And that's produced over the course of a year. And that's just the optical light. That doesn't include like the X-rays and the gamma rays and all other stuff. That's just optical light, 10 to the power of 42 joules. And like, how much energy is that? So I did a little bit of back of the envelope math to figure out, to maybe get that into a unit that we can understand marginally better. And what that turns out to be is this obscene number, which is, it's equivalent to 10 billion Hiroshima detonations every second for the age of the universe. That's just the optical light. We actually get another 10 to the power of 44 joules, so a trillion Hiroshimas per second for the entire age of the universe in the kinetic energy of the ejected material. So all the material that was in the star that gets blasted out into space, just like unimaginable amounts of energy. Now, as a result of this, you have a lot of neutrons flying around, like a lot of them. And so we get more elements up the periodic table through the R process, so the rapid neutron capture process. So in fact, the amount of neutrons produced in a supernova is 10 to the power of 24 per cubic centimeter, which is also insane. So they get captured very easily. Those decay into protons, and you keep stepping up the periodic table that way. You get a lot of iron and nickel in this process, and sometimes this process gets high enough to reach uranium for a few seconds during the explosion, which is insane. Now, a single type 1a supernova produces a sun's mass worth of nickel, which now this is a weird isotope of nickel that decays to iron, and half of the iron in the universe is produced this way. So if you have think about all the iron you've encountered in your life, made in a supernova. All right, where else are these heavier elements made? Because when I was first building this talk, it's actually a relatively new understanding that a lot of the heavier elements are actually made in neutron stars, which is really cool. So yeah, as you can see here, everything that's purple is made in merging neutron stars, which I'm about to talk about, and all the stuff in yellow is from supernovae. We used to think that a lot more stuff was made in supernovae, but now we know that actually a lot of it is made in neutron stars. All right, so first of all, what are neutron stars? They're the dead cores of post-supernova stars. So not all stars that go supernova become neutron stars, but especially the big ones that have big supernovae will tend to leave behind a neutron star core. After the supernova, the dense core continues to collapse, which pushes the protons and electrons that are present in there so close together that a different kind of beta decay occurs that converts protons back to neutrons. Now, neutron stars, for the fact that they're a star, are really small. They tend to only be about 12 to 20 miles across, so like the size of a city. And a single teaspoon of neutron star material weighs 1 billion tons. Like this stuff that happens is just insane. They also, in addition to all of this craziness, they rotate thousands of times per minute sometimes, and which is the result of a lot of the energy of the supernova being converted into rotational energy. And these are known as pulsars. Now, we've proven the existence, now we can't like observe neutron stars like with a telescope. We've proven the existence of them thanks to gravitational wave discoveries, as we have watched neutron stars merge using facilities like LIGO that can see these gravitational waves. And now we have a lot better idea where a lot of the periodic table comes from as a result. And so because merging neutron stars and actually merging black holes as well are very neutron-rich environments, there's a lot of opportunities for that R process to occur, where elements that were still kind of in the outer part of that neutron star that were things besides neutrons, like we still have things like iron and lead and carbon floating around in there. They can collect a whole bunch of neutrons, which beta decay to a whole bunch of protons in these nuclei, which again steps up and up the periodic table. Now, I was asked a question the first time I gave this talk at the Texas Star Party. Well, if they're around the neutron star, how do they get out of the neutron star? And this question actually stumped me. So I went and looked it up, and it come to find out just a month before I gave the talk, it had been discovered that these elements that were made in neutron stars got out of them because of these neutron star mergers. So that's pretty recent science, which is really cool. It's now known that the majority of heavy element material in the universe are made in these violent neutron star mergers, including the majority of gold and platinum. So your Redding ring isn't just star stuff, it's particularly merging neutron star stuff. So it's like one step cooler. So it is from all of these events, starting all the way back in the Big Bang, where we just have hydrogen and helium floating around, finally forming some stars, finally, those stars being able to make things technically up to iron. They don't make it up there very often, but sometimes it happens. And then in the dying stars and planetary nebulae, there being enough neutrons around to keep going up the periodic table, in supernovae, in merging neutron stars. And as older stars die and spew all those heavy elements across the universe, they get absorbed into new stars like our sun. And as the sun is forming itself, there's a lot of leftover material, a lot of leftover carbon, a lot of leftover hydrogen and oxygen and nitrogen and all kinds of stuff, even all the way up to uranium that is part of this protostellar cloud. The star forms, and it forms its solar system, and planets start to form, and people evolve on this planet, and we finally get to where we are now after this long journey of hydrogens fusing into heliums and capturing more and more neutrons and going through birth and death cycles of stars, all the way until it somehow makes it into a ball and we come to exist to learn to understand the process. And that is the story of stellar nucleosynthesis. I know it's a lot, so I hope you wrote down your questions and I'll take questions now, which I'm sure you have many.
Just remember to unmute yourselves, folks.
Very, very good.
Thank you.
Okay, let's see. Who's got the first question? How about Paul? Paul Huntley?
Yep. Hi, thank you for the talk. It was great.
Thank you.
I have a question about the cosmic web and how that formed. I guess, like during the age of recombination, when there's real matter, but how does the distribution get into the web?
So you're talking about the cosmic microwave background?
Well, I don't think so. I'm I'm talking about the the tendrils of gas and dust at whose intersections galaxies first formed.
Right. So it actually stems all the way back to far before recombination. This is the current thinking, at least, all the way back to shortly after the Big Bang, that there was a clumpiness to that. I can't remember if it's at the time of the quark gluon plasma, or if it's when we start having protons and neutrons. Sometime around there's kind of a lumpiness when the universe is still very small. So yeah, it must have been during like the quark epic, or actually no, I think it was possibly before inflation. I can't remember exactly offhand. Sometime in like the first less than a minute of the universe, is kind of a lumpiness in the quark gluon plasma. And when the universe expands, that lumpiness of material remains.
Mhm.
And we think that that's the basis of this web of like if you see the computer simulation images where we have these kind of lines of superclusters and it almost looks like a sponge. I think that's what you're talking about.
Yeah.
We think it traces all the way back to that very early time, but that's still not well known. That's kind of the prevailing theory that I'm aware of, at least.
Fascinating. Thank you.
Yeah.
Isn't it dark energy and dark matter?
Yes. I could do a whole talk on this too. I'll quickly describe how the ideas of dark matter and dark energy came about. So dark matter, so when you look at how a galaxy rotates, it doesn't rotate like imagine putting like a t-shirt on the floor and twisting it, and like the spirals get tighter and tighter as you twist it. And that was long thought to be why galaxies had spiral arms. But then as observational astronomy came to mature, we observed that galaxies actually rotate like frisbees, where the whole thing rotates at the same time. But that doesn't make sense, because we can see by the amount of light in the galaxies, we can see the mass distribution through the galaxy. We know that there's more mass in the core and less mass toward the edges. And so having something spin like a frisbee doesn't make sense when there's less mass toward the edges and more toward the center. So that's where the idea of dark matter arose, where there's matter that's not emitting light, but has mass that is a little more concentrated toward the parts of the galaxy that have less visible mass, and that's why they spin like disks. So that's the basis of dark matter. There's been a lot more observations since then. And the basis of dark energy is the fact that, so after inflation, you have the competing forces of the energy, the leftover energy of like the intense force of inflation, competing with the attractive force of gravity. And so one would think that we're gonna, like after inflation, it expands, but the rate slows down. But that's actually not what we observe. The rate of expansion is actually speeding up. But in order for that to happen, there has to be an energy source that is going into that counteracts gravity. And that's what we call dark energy. We don't know a whole lot about it yet. We know far less about dark energy than we know about dark matter, actually.
Is this an expansion based on the redshift?
Yes. So yes. Yeah. So yeah, based on observations of the redshift and the Hubble constant, as it's called. So kind of the expansion rate of the universe. As far as knowing that it's expanding at an increasing rate, I'm trying to remember how we determined that. Oh, it's not coming to me right now. But through some sort of observational astronomy, we have determined that it is definitely expanding at a faster rate. I don't think that's really in question, but I don't remember what the kind of experiment chain was to determine that offhand.
Yeah, the thing that I thought about is that the photons traveling that far and that far back in time slows down. Wouldn't that cause a redshift?
So
Because the speed of light is not constant. I mean, through a vacuum it is, but like through water or through material, it changes. So based on the distance, 13.8 billion years, the photons, wouldn't it slow down after traveling that distance?
So the slowing down in water is because of the material. It's traveling through. It's having to bounce around and and get absorbed and re-emitted by all of the molecules that are in water, for example. Out in the universe, it's enough of a vacuum where you're not having that index of refraction of that would slow down that speed of light. So instead,
what about dark matter? No.
So dark matter doesn't interact with light. That's why we can't see it. So the light's not being affected by the dark matter at all because the dark matter doesn't interact with light. So what we're actually seeing,
we don't really know that though, because
if dark matter interacted with light,
exist.
well, if dark matter
but gravity too.
If dark
There's
matter
also
interacted
gravity
with light,
too.
we would be able to see dark matter.
Okay. But gravity too would affect it because we see gravitational lensing.
Yes. So dark matter only interacts via gravity, and
exactly.
That is why we can see one of the ways that we have observed dark matter is by gravitational lensing. You're absolutely right. As far as the why light that is from further away is lower energy, it's not moving slower, but it's redshifted, which is the wavelength of the light has been stretched, like taking a rubber band and stretching it out, because space itself has stretched and the light stretches along with it. And that's the cosmological redshift that is partly why the cosmic microwave background is at radio wavelengths in the current era, and also why galaxies that are very far away are much redder, and that's why we need to use James Webb to look in the infrared, for instance, to see those very early galaxies. So the photons are still traveling at the speed of light, but their frequency, their wavelength has been stretched. It's a very weird concept. So
Molly has the concept of modified Newtonian dynamics as an explanation to the spin in the galaxies been pretty much now poo-pooed?
Yeah, it's been largely dismissed.
Okay.
It's kind of seen as a fringe view.
Mm-hmm. Okay.
The way I looked at the spin of the galaxy is, say you got a bowl of water and you would use soap in it and then blow a whole bunch of bubbles in the middle. And then if you were to take that set of bubbles and spin it around, they'd be all connected to each other. So as these galaxies are spinning, gravity of all the stars together are connected to each other. So the rotation of the massive bubbles will spin like a galaxy because they'd be all, the bubbles are connected to each other through their cohesion. But the way I see it on the galaxy is the gravity of the mass of airy stars and the matter that's in there is all cohesion connected by gravity.
Yeah, although if you made a bigger bowl, you would see that the edges of as you get out toward the edges of that bowl, that outer ring of soap bubbles would be spinning slower than the middle.
Mm-hmm.
I mean, the bubbles are adhering to the edges of the bowl, so that kind of complicates the experiment a little bit. But let's say the bubbles, let's say you had food coloring in there instead, so it's not adhering to the side of the bowl as much.
Well, there is a limit to the size of a galaxy, right?
Yes, yeah, I'm talking about to the size of the galaxy. Actually,
Yeah.
I just heard earlier today that we've discovered a galaxy that's like 16 million light years across. Put that in comparison to the Milky Way, which is 100,000 light years across. There's not a maximum size for
Yeah,
galaxies?
but how big is the black hole in the middle, though?
That's an excellent question. It's probably ridiculous.
Yeah, yeah. I had a theory that when I was back in college that all galaxies had a black hole in the center. Of course, everybody laughed at me back then, but
Yeah,
I figured that
come to be
what can
true.
have so much gravity to hold the galaxy together,
Yeah,
and that's when back then I came up with that theory.
yeah, and that's come to fruition.
Yeah, now we find out it's true.
Yeah. Not interestingly, not all galaxies have a black hole at the center. Some of them don't. But I think the ones that don't tend to not be kind of normal galaxies. They're like your ellipticals and stuff that was probably the result of galaxy mergers.
I had a question that pertains to astrophotography.
Yeah.
We have the hydrogen, oxygen, and sulfur. You didn't mention sulfur in any of that, but are those three the main ones just because their emissions are in the visible spectrum? Is that kind of why we have those three main ones?
Yeah. So sulfur is I mean, it's definitely made in stars, but it's not in any of those kind of standard processes like the PP chain and the CNO cycle and stuff like that. So good observation. The reason why it's more prominent is, yes, because it's in the visible spectrum, and also tends to be a particularly bright emission. I guess more photons are released. Well, I'll say it doesn't make sense. I think it's primarily because it's in the optical spectrum. Yeah.
Any more questions?
Yeah, hey Molly, that was fantastic, by the way.
Thank you.
Yes, my cat's here too.
Yeah, I noticed that. I meant to mention it earlier.
Oh, and she's gone. Quick question on microwave background.
Yes.
Okay, obviously microwave background is a very low energy level. What was it when it was originally released? Are we like gamma ray, X-ray? Where were we?
So since the universe was about 3,000 Kelvin at that time, so that's that 379,000 years, 3,000 Kelvin temperature.
Mm-hmm.
3,000 Kelvin is roughly like yellow red on the color spectrum, so it would have been visible light.
Okay, thank you.
Which is really cool.
It is.
They show the classical picture of the atom, but it would make more sense if instead of the electrons zipping around in their orbits is just to be cloud around
That's right.
the nucleus.
Yes.
Yeah, field.
Yeah, it's a probability cloud because those electrons, you get some quantum effects coming into play where you can't know the position and the speed or the energy of the electron at the same time. So you have this probability density, you have this probability distribution of where they could be at any given time throughout around the space of the atom.
Question.
Yeah.
I don't know if this is in your wheelhouse or not, but I have a Celestron 8 SE with a hyperstar.
I have one of those, yeah.
And I love it. I'm actually shooting stuff right now as we talk. I'm kind of halfway distracted. And kind of going through the big filter dilemma, and not just the 1 1/4 versus 2 inch, but the fast, f2 plus filters. And I've seen some stuff online regarding it has to do with the tilt of the filter that makes it where it doesn't work. I mean, do you have any input on that? What makes a filter better for shorter focal ratios versus longer? And
I was just looking this up because I was curious. Because I don't have a hyperstar, but I have a fast camera lens. I have one of those Rokinon f2 lenses, and I did observe that. So I used a regular a narrowband filter that wasn't specifically for fast systems. And while I still got a reasonable image, I did notice that my light was a lot dimmer than I expected. Based on like having used that same filter with my refractor, for example. So that effect of the light, less light coming through is real. I was looking this up. It has to do with, so let's see. So I know that for really narrow band passes, say like 3 nanometers, the effect is much more severe than say like an 8 nanometer filter.
Yeah, the optolong L extreme versus the L
Yeah.
enhance. I heard it really is
Yeah, and
bad.
apparently because there's a bit of a there's a wavelength shift with really fast optics, because I think it has to do with the fact that you're taking in light rays from more angles or something like that.
Is it almost like a polarizing effect?
No, not a polarizing
No,
effect.
it's not a-
Not in this
Okay.
case. You get a bit of a wavelength shift because something to do with the optics of being at f2.
Okay.
But I was looking this up, but I can't remember.
Yeah. It
What's a
causes
good-
problems.
What's a
Yes,
good
yes.
narrowband filter for a color camera?
So, for a color camera. Well, so in reference to the fast systems, the like Hyperstar, I recently got an IDAS filter. What was it called? I can't remember which. There's a filter from a company called IDAS that is made for fast focal systems. In general, for color cameras, if you're in a light polluted area, there's going to be 2 kinds of filters that you want. One is a light pollution filter, and for that, my personal recommendation is either the Astronomy CLS-CCD or the Optolong L Pro.
Optolong L Pro.
I just got an L Pro myself, but I haven't processed any images with it yet. So I want to compare the L Pro to the CLS-CCD.
I just picked up a LPS D3 and yeah. And the high speed ones are the NBZ UHS ones.
That's the one. Yeah. I have like an IDAS NBZ something. So a lot of people love their L Pros, and I've loved my Astronomy CLS-CCD, gotten great results out of it. Looking forward to getting good results out of the L Pro. Now, so that's on the light pollution side. On the narrowband side of the house, so you can do narrowband imaging with a color camera, and that's best done with a multi-band pass filter instead of like putting just a hydrogen or just a oxygen. I use the Optolong L Extreme, gotten great results out of it. I have not yet tried that IDAS filter, and IDAS makes that same filter for like regular focal length systems as well. So, but people love their L Extremes and their L Enhances. Optolong makes some good stuff, I guess.
Let's give this a try. Can you guys hear me?
Yes.
Yeah.
Okay.
We finally got you. Yay.
Well, I didn't get a chance to test anything before this meeting started. I kind of just jumped in the middle here, well, after the first 10 minutes, so I didn't want to interrupt anything like that. Back to the original discussion, and all your stuff went away, but that's okay.
I can bring it back up.
That's okay. It's the last part there is where the larger elements were made.
Yeah.
And that time period isn't very long compared to the rest of the time. But how many iterations of supernova, stars, so on and so forth, would it have taken to get enough elements to make our solar system, say, and then any other solar systems that might be around us? And is there any way to trace back to see if there's any remnants anywhere else of the same stars or supernova?
Yeah, it's a good question. So a single supernova, even if it's from like an early star that only had hydrogen and helium, through the R process can produce elements all the way up to uranium. It doesn't need to have been seeded with heavy elements for that to occur, because there's such a density of neutrons flying around that R process can happen rapidly, and you can run up that mass chain. Now, a lot fewer of those are, like, the further up that mass chain you go, the fewer that are being made, because it does take some time to get up there, because it takes time for these beta decays to occur. So I think theoretically one, because but to get enough material to make a planet. So all the stuff that's produced in a supernova is going to go flying out into space, and it's going to take probably more than one supernova's worth of material just to have enough kind of material in a given area for a star to start to collapse, to start to form. I don't know if that question's been looked into. I'd be curious to go see if anybody's kind of done some simulations on that, because it would depend on like supernovas per unit area, per unit volume, what force the material is blown out of. Say again?
There were supernovas in the beginning, right?
Yes. Yeah. Those early stars didn't last very long.
I was watching the one show, you know, like a Nova and other ones. They're saying that we're like third or fourth generation supernova.
You got really quiet at the end. Can you say that again?
I said some of the shows I was watching, they were saying we're about the third or fourth generation.
Okay. Yeah, that's interesting. I will say that there's kind of three populations of stars that are ranked by their metallicity. Now, in astronomy, it's a little funny because everything that is heavier than helium is considered a metal, to include oxygen and things that are obviously not metals. So astronomers refer to anything heavier than helium to be a metal. And as the first population of stars, which is counterintuitively called population 3, those are made of just hydrogen and helium. They went supernova. They generated some of those heavier elements. Those eventually collapsed to form new stars. So those stars started out with some carbon and oxygen and nickel and stuff like that. Not necessarily fusing them, but they were there in that star. And then eventually that star, that set of stars, population 2 stars that are low metallicity but have some metals, are going supernova. Now there's still plenty of population 2 stars out there, but they're older stars. And those go supernova and produce even more of the metals and things like carbon and oxygen and whatnot. And those go on to seed population 1 stars, which is like our sun. So they have a much higher amount, they're seeded with a much higher amount of these heavier elements. And because it's in the stars, it's also going to have been in the protostellar disk where all the planets were formed. So you can think of it as 3 generations of stars, but it's a little more complicated than that because they're going supernova at all different kinds of timelines. So as far as like number of individual supernovas to make a planetary system, I have no idea. 3 or 4 sounds like a likely number.
Okay, looks like you're going to school.
Our galaxy is not as old as the universe.
Our solar system definitely isn't as old. Our galaxy's not among the first galaxies, but there were population 3 stars here at some point in the past. We keep looking for them. Well, we don't look for them here because they've all died out. We look for them in distant galaxies. Presumably they were here at some point.
In your illustration from the Big Bang to the today thing, the last section is the section where this all happened. How far into that section are we when we were created, I guess would be the best way to put that.
So the solar system, first stars and galaxies form 300 million to 500 million years after the Big Bang. Our solar system, so the sun was formed 5 billion years ago, so 4.5 billion years after the first galaxies and stars. No, sorry, I got that backwards. Let's see, what's 13.6? 13.8 minus 5 is 8.5 minus so like 7 billion years after those first stars and galaxies, we finally get our star. And our planet is roughly 4.6 billion years old. And then of course humans don't show up until 120,000, 200,000-ish years ago. I think it was I don't know if Carl Sagan did it first, Neil deGrasse Tyson or somebody, but if you put the entirety of the age of the universe on a 24-hour clock. Humans appear, so like you start at midnight, you go around to noon, you go around almost to the next midnight. Humans appear about 30 seconds before midnight in terms of the age of the universe.
Yeah, I think I've seen that.
Yeah, it's really
I think I saw that in Carl Sagan's original Cosmos.
Okay, yeah.
And
Does that
thank
answer
you,
your
Molly.
question?
And thank you, Molly, for confirming something. I think I had figured it out, but I was confused for the longest time. I would read about metal-rich stars, and they were younger stars.
Yeah.
And I thought that made no sense, because I was thinking as stars get older, they're fusing hydrogen to helium all the way up to iron. So I was thinking, aren't older stars metal-rich? Then I finally figured out what they meant.
Yeah. So that's also true. Like as stars get older, they're having to fuse heavier things in order to stay alive. So both of those things are true. But yeah, the metallicity is how they were seeded, largely.
So, hey, Molly, does our sun having certain amounts of metal, is it just you just very classically with the spectrophotometer or whatever, you could tell how much % of these different metals we have in our sun? Is that
yes?
Is simply that way? Yeah.
That's where the lovely art of spectroscopy comes into play, and not just on the visible spectrum, but across the spectrum. We can tell the abundances of all these different materials in the star based on the light from the star.
Well, it's what the star is actually burning up, not necessarily what it's made out of, though.
Well, so there's going to be emission lines and absorption lines. So if the star is fusing hydrogen, that energy is made in the core of the star, but it has to make its way to the surface. Yeah. And in the course of that, it's going to bounce around and be reabsorbed and re-emitted. And for those metals that are going to absorb on a particular wavelength, that wavelength is going to be missing from the spectrum. So we look at not only emission, but also absorption.
Ah, okay, good.
Yeah.
Thank you. That makes sense. Thank you.
Any more questions? This is a great discussion.
Yeah. This is
don't want to keep Molly up all night though. We're talking about
she's got a lot of photos to still take. Okay, she's got hours.
Oh, it's all running automatedly.
Yeah, it's after midnight back there.
Let me double check that there's any questions in the chat, but it looks like it's just people. Oh, cats versus dogs. All right.
Yeah, I'm anxious to my little Red Cat 51. I got a L Pro filter for it just the other day, so I haven't tried it out yet. So it'll be fun to try it.
They really do make a big difference in the city. A little less of a difference now, unfortunately, as a lot of cities switch to LEDs. And I have actually observed this in my yard. But I have still observed that when I use just a luminance filter versus a light pollution filter, one really clear instance of this is I was polar aligning my telescope one night, and out of curiosity, I think I tried one of my other filters, and I could see the clouds very clearly, like when I was just kind of looping my camera. I could see them very clearly, reflecting the city light with the luminance filter. But then when I put in the light pollution filter, most of that light went away. So it is helping.
Jerry, did you have a question? I saw a hand up. You're muted. You're muted.
No, I did not have a question. I'm sorry.
Oh, okay.
That was just the raised hand from the
well, that's the applause
reaction. Yeah, actually, that's what it
is. Great. Okay. Do we have anybody else with questions before we let Molly get back to her imaging?
back to my sleeping.
Well, I certainly want to thank you for an excellent talk. You know, it's nice to see the big picture, and you did a great job on that.
Thank you.
From start to finish, here we are.
I know I threw like a lot of science at the wall, but hopefully some parts of it at least are a little clearer.
Yeah, that's well. Let's all give a hand to Molly. This was just a great presentation, as usual.